particular problem, then almost we will take everything. Okay, what type of questions he is asking, and everything I just explained in one single problem. Okay, now we will solve the other problems also. So, but all are same as that of the first problem. Now this is the transfer function g of s, which is equal to k by s into s plus 1 into s plus 2 into s plus 3. Okay. Now this is first comes under which category? Now there are four poles. There are four poles, and how many zeros? No zeros. What is the difference between poles and zeros? Np minus Nz, 4 minus 0, which is equal to 4. So the difference between poles and zeros are 4. Therefore, this is number of poles are 4, number of zeros are 0. This is a practical transfer function. If it is a practical transfer function, you have 3 points. What is the first point? Complete root locus branches. Complete root locus branches are NP, which is equal to 4. Second point, how many branches terminates at infinity? Terminates at infinity is NP minus NZ, which is equal to 4 minus 0, which is equal to 4. Now, how many branches terminates at 0? Terminates at 0 is Nz. Nz is nothing but 0. Now the number of branch terminates at infinity is Np minus Nz, which is equal to 4 minus 0, which is equal to 4. Now see here. Now the total number of angle of asymptotes. The total number of angle of asymptotes are 4, Np minus Nz. What is the first angle of asymptote? The first angle of asymptote, which is nothing but 180 degrees by Np minus Nz, which is equal to 180 degrees by 4, which is equal to plus 45 degrees. Now what is the second angle of 45 degrees into 1, which is equal to 45 degrees. What is the second angle of asymptote? The second angle of asymptote, which is equal to 45 degrees into 3, which is equal to 135 degrees. And the third angle of asymptote, which is equal to 45 degrees into 5, which is equal to 225 degrees. And the third angle of asymptote and the fourth angle of asymptote, 45 degrees into 7, which is equal to 315 degrees. But all these things are not required. I am giving only one point to you. The angle of asymptotes are always symmetrical about the real axis. What I am saying? The angle of asymptotes are always symmetrical. If one angle is plus 45 degrees, definitely another angle is minus 40. It is existing. If one angle is 135 degrees, definitely the other angle is minus 135 degrees. Angle of asymptotes are always symmetrical. Okay. Now this is plus 45. Now this is 315 is nothing but minus 45. This is 135. This 225 degrees is nothing but minus 135. What I am saying? This angle minus 360 degrees. This angle minus 360 degrees, because the total angle is nothing but 360. This minus 360 is minus 135. This minus 360 is minus 45. Okay. Now the angle of asymptotes. Once the angle of asymptotes are completed, next is centroid. What is the centroid? Sigma. The centroid, which is nothing but sum of the real parts of poles. Sum of the real parts of poles. 0, minus 1, minus 2, minus 3 by sum of the real parts of zeros. 0 by Np minus Nz is 4. Therefore, minus 6 by 4, minus 3 by 2, minus 1.5 is the centroid. Okay. Then now we'll start the same normal procedure. Now locate the poles and zeros on S plane. one pole is at origin, one pole is at -1, one pole is at -2, and one more pole is at -3. Identify the root locus branches. This is the root locus branch, odd number. No root locus branch, even number. Now this entire this section is also a root locus branches. Okay. Now centroid, where is centroid sigma? Now the centroid, which is nothing but sigma, which is -1.5. Now you can see here, the centroid is now not on the root locus branch. It is on the real axis. The centroid lies anywhere on the real axis. It may be on the root locus branch or it may not be on the root locus branch. Now the angle of asymptote. What is the first angle of asymptote? Now the first angle of asymptote is 45 degrees. This is the first angle of asymptote. And you immediately draw the -45 degrees because angle of asymptotes are always symmetrical. Next, another angle is 135 degrees. If one angle is 135 and another angle should be -135 because the angle of asymptotes are always symmetrical. This is one angle. This is another angle. So the angle of asymptotes are always symmetrical. Always symmetrical. Okay. Because the poles zeros locations are with respect to real axis, therefore the angle of asymptotes are always symmetrical. Now these are the angles of asymptotes which are showing the direction approaches to infinity. Now see here, the root locus diagram starts with k equal to 0, starts with open loop pole. The root locus diagram starts with k equal 0, start with open loop pole. As k is changing, closed loop pole is moving. As k is changing, closed loop pole is moving. These two closed loop poles are meet at a particular point. That particular point is called as breakaway point and leaves with an angle of plus or minus 180 degrees by n, which is equal to plus or minus 180 degrees by 2 plus or minus 90 degrees. Now one is plus 90 degrees, another one is minus 90 degrees. Now, and it will follow the angle of asymptote. And it will follow the angle of asymptote. If you go in this particular direction, definitely you will meet 1, 0. The root locus branch terminates with open loop 0, terminates with k equal to infinity. Now as k is changing, closed loop pole is moving. As k is changing, closed loop pole is moving. The root locus branch terminates with k equal to infinity, terminates with open loop 0. Now, the root locus diagram, no root locus branch here. The root locus branch terminates with k equal 0. The root locus branch starts with k equal 0, starts with open loop pole, starts with open loop pole. As k is changing, closed loop pole is moving. As k is changing, closed loop pole is moving. Now these two closed loop poles are meet at a particular point. Now this particular point is called as breakaway point, again with plus 90 degrees and minus 90 degrees. Now this is leaving, and it will follows the shape of angle of asymptote, and it will follows the shape of angle of asymptote. Now in this direction, the closed loop poles are moving and the root locus branch terminates at k equal to infinity, terminates with open loop 0. terminates with k equal to infinity, terminates with open loop series. Okay, this is very simple. Now see the shape of the root locus diagram, which will follow the angle of asymptote. Okay, now just draw this root locus diagram. Okay, now here is one important point you want to be identified. Now this is the breakaway point. You know how to find the breakaway point. This is the breakaway point. This is breakaway point 1. This is breakaway point 2. Here gain you find some K1. Here gain you find K2. You know how to find breakaway point. You know how to find gain and everything. You know that. Okay. And whatever we are doing for the first problem, you do for the same thing. You have a good practice for this particular problem. Now when this is underdamped, overdamped, critical damp, and what is the conditional stability, when this root locus branches intersects, what is K margin, what is frequency, right? All the possibilities you can easily find. But a few important points. Now this is correct or not. Now without drawing the diagram also, we just check. Complete root locus branches are how many? 4. But how many are in the problem? Starts at poles, ends at 0. 1. Starts at poles, ends at 0. 2. Starts at poles, ends at 0. 3. Starts at poles, ends at 0. 4. Now how many are the complete root locus branches? 4. Is matching or not? How many branches terminates at infinity? 1, 2, 3, 4. How many? 4 is correct. Now, how many branches terminates at 0? There is no 0 in the transfer function. Therefore, no branch is terminating at 0. Clear or not? All are correct or not? So, like that you can easily identify. And one important point. Now, where is the centroid? Now, the centroid is minus 1.5, which is not on the root locus branches. Therefore, a few important points I want to be share to you. Now, the first important point, the centroid lies anywhere. Centroid lies anywhere on the real axis. Centroid lies anywhere on the real axis. It may be or may not be, it may be or may not be on the root locus branches. It may be or may not be on the root locus branches. Second point is breakaway point and break-in point must and should lies on root locus branches. And another important point, the root locus diagram is always symmetrical about the real axis. Is always symmetrical about the real axis. The root locus diagram is always symmetrical about the real axis. Now with respect to real axis, now how the diagram, it should be a symmetrical diagram with respect to the real axis. The root locus diagram is always symmetrical about the real axis. Because the angle of asymptotes is always symmetrical. The angle of asymptotes is always symmetrical about the real axis. The angle of asymptotes are always symmetrical about the real axis. Okay, these are the few important points while you are drawing the root locus diagram. So if the root locus diagram is any symmetricity is not maintained with respect to real axis, that diagram is 100% wrong. Angle of asymptotes are always symmetrical, therefore the root locus diagram is always symmetrical. And the shape of the root locus diagram will be same as that of angle of asymptotes. Understand? Now note down this particular few points. Okay, for this particular problem, now you solve everything: breakaway point, break-in point, gain at breakaway point, gain at break-in point, and when it is over-damped, under-damped, critically damped, everything you can easily calculate. Now g of s equal to k into s plus 2 into s plus 4 by s square plus 2s plus 2. S square plus 2s plus 2. Now the pole's location. Now first locate the poles. Now these are the complex conjugate poles. And these are the zeros. 1 0 is at -2, 1 0 is at -4. These are the complex conjugate poles. Now this is the root locus branch. Now here, and most of the students are doing the same mistake. Now complete root locus branches NP, like that you are writing. No, this is not valid for this. This is valid only for practical transfer function. These three shortcut methods are valid only for the practical transfer function. The practical transfer function is a transfer function where the number of poles should be greater than the number of zeros. This is valid only for the practical transfer function. But the given transfer function is an ideal transfer function. Number of poles is 2, number of zeros is 2. This is only for ideal transfer function. I am talking about the practical transfer function. The practical transfer function, then these 3 points are comes to picture. For ideal transfer function, no, nothing. Now the question is, we know only one thing. There is no practical transfer function. Number of poles and number of zeros are same. Sir, what happens if the number of poles and number of zeros are same? If the number of poles and number of zeros are same, which means that NP equal to NZ. If NP equal to NZ, which transfer function? Ideal transfer function. If it is the ideal transfer function, what happens? If it is the ideal transfer function, there is no angle of asymptotes, because 2q plus 1 into 180 degrees by NP minus NZ, something by 0, infinity, and there is no angle of asymptotes. There is no centroid. If the angle of asymptotes are available, then we can guess the shape of the root locus diagram. But there is no shape of the root locus diagram. I cannot guess because there is no angle of asymptote. If angle of asymptote is not there, there is no centroid, because 2q plus 1 into 180 degrees by NP minus NZ, 0, something by 0, infinity, some poles minus some zeros by 0, this is infinity. No angle of asymptote, no centroid, and there is some problem because I don't know the shape of the root locus diagram. Even if you don't know the angle of asymptote, even if you don't know the centroid, we will try to draw the root locus diagram by starting from the poles and ending at zeros. Okay, this is one important. If it is ideal transfer function, no angle of asymptote, no centroid. Okay, there is no angle of asymptote, no centroid. Now take down this. So now we want to take a problem which comes under ideal transfer function. So whatever it may be. So we know that only one thing. The root locus diagram starts at poles, ends at zeros. Starting means I want to start here, 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 like that. How many directions? If the root locus diagram starts at poles, infinity directions. That's why here we want to do one thing. So the root locus diagram starts at complex conjugate pole. Now with some angle, you measure those angles. That is nothing but angle of departure. What is that? That is called as angle of departure, theta d. Angle of departure. Now what is angle of departure? This is the angle. Now angle of departure. This is the angle at which the root locus branches leaves at complex conjugate pole. This is the angle. This is the angle at which root locus branches leaves at complex conjugate pole, and the angle of departure is calculated at complex conjugate pole. Now this is the few important points. The departed angle is calculated at complex conjugate pole, and that is the angle at which the root locus branches leaves the real axis. These are the two important points. Therefore, now I want to measure the angle at complex conjugate pole. Now this is the reference complex conjugate pole. Where we want to measure the angle of departure. And most of the students are saying that, sir, why you are taking this is the angle of departure reference complex? Why you cannot take this as a reference? Both are same. These two are the symmetric angle. Here it is 10 degrees minus 10, 100 degrees minus 100, 40 degrees minus 40. Am I right or not? So that's why you can take a complex conjugate pole as a reference angle. Now listen carefully. Where you want to find the angle of departure. Now that is the reference complex conjugate pole. From all the poles and zeros, you draw the vector lines. From this pole to the reference pole, if I draw a vector line, and this is angle made by pole P. And from 0 to this is the angle made by 0, 1. And from this 0 to this is the angle made by second 0. And if one more pole, angle made by pole P1, P2, P3, more zeros, angle made by zeros, G1, Z1, Z2, Z3, like that. So measure all the angles made by poles and made by zeros with respect to reference complex conjugate pole, where we want to measure the angle of departure. Okay. Now, what is pi p? This is, let us assume pi p1. This is very simple. Pi p1 is nothing but simple 90 degrees. Now what is pi z1? This is the reference. Okay. Now this reference is, this is minus 1 plus j1, minus 1 minus j1. This is the complex conjugate, minus 1 plus or minus. This is minus 1 plus or minus j1. Right. So now what is phi z1? So you can calculate only phi z1 separately. Now if I write here phi z1 separately, this is pi z1. Now this distance, because this is the real part, this distance is 1 and this distance is also 1. Therefore what is phi z1? The phi z1, which is equal to tan inverse 1 by 1, which is equal to 45 degrees. This is phi z1, which is tan inverse 1 by 1, which is equal to 45 degrees. Now what about this vector distance? This is pi z2. Now this vector distance is 3. Now this vector distance is 1. Now this is pi z2, which is equal to tan inverse 1 by 3. Now see here, this distance is 3, this distance is 1, tan inverse 1 by 3, which is, this is 18.43 degrees. Okay. This is 5. Like that you can measure all the angles made by poles and all the angles made by zeros. And after that you will find phi. What is phi? Phi is nothing but sum of the angles made by poles, sum of the angles made by poles and sum of the angles made by zeros. Now this is the sum of the angles made by poles minus sum of the angles made by zeros. Now this calculation is with respect to complex conjugate pole. Now, what is the sum of the angles made by poles? The sum of the angles made by poles is nothing but this is pi p1 only minus sum of the angles made by sum of the angles made by zeros is pi z1 plus pi z2. Now, which is nothing but 90 degrees minus of 45 degrees plus 18.43 degrees. Therefore, this is nothing but 26 point now this is 45. Now this is 18.43. So this is 26.57 degrees. Okay, 26.57 degrees is 5. Now the angle of departure. Now the angle of departure theta d. Now the angle of departure theta d, which is nothing but this is the departed angle, leaving angle. Therefore, 180 degrees minus 5 is the angle of departure. So this is the angle of departure, which is nothing but theta d, which is equal to 180 degrees minus 26.57 degrees, which is equal to 153.43 degrees. 153.43 degrees is the departed angle. With that particular angle, the root locus branches leaves the real axis at complex conjugate pole. Okay. Now we first take this one. Okay. Now once you find the angle of departure, now you can easily draw the root locus diagram. Now this is the complex conjugate poles, which is minus 1 plus or minus j1, minus 1 plus j1 minus 1 minus j1, and this is the zeros at minus 2 and minus 4, and this is the real axis. Between this section is the root locus branch. Now the root locus diagram starts with k equal to 0. The root locus diagram starts with k equal to 0. The root locus diagram starts with open loop pole. Starts with open loop pole. Right? Now with an angle of, this is 0, this is 90, this is 180, exactly middle is 135, right? And this is 153. Now, this is the angle at which the root locus branches leaves the complex conjugate pole. This is 153 and this is minus 153. This is the angle of departure. Now, as k is changing, closed loop pole is moving. Now, these are the root locus branches. Now, see here. Now, there is two adjacently placed zeros. There is two adjacently placed zeros. Between them, there is a root locus branch. Between them, there is a root locus branch. And definitely, there exists one break-in point. Am I not? Definitely, there exists one break-in point. Now, and with what angle the root locus branches enter into the real axis? Now, this is enter into the real axis with an angle of plus or minus 180 degrees. This is called as the root locus branches enter into the real axis or leaves that real axis at an angle of plus or minus 180 degrees by n. Therefore, this is the departed angle and enter into the real axis. This is the departed angle and enter into the real axis. As k is changing, closed loop pole is moving. As k is changing, closed loop pole is moving. As k is changing, closed loop pole is moving. And as k is changing, closed loop pole is moving and terminates with k equal to infinity, terminates with open loop 0. Terminates with k equal to infinity and terminates with open loop 0. Now, the root locus diagram starts at poles, ends at 0. Starts at poles, ends at 0. Now, with this particular angle, and this particular point is called as break-in point. This is the break-in point. Okay, and there you can find the system gain also. You will find some system gain that you know how to find the break-in point. Now, this is the break-in point. You know how to find the break-in point, and you know how to find the gain at break-in point. And you know how to find the gain at break-in point. That is the break-in point, and you know how to find the gain at break-in point. Okay. Now, this is the root locus diagram. Not only root locus diagram, and this is the way to find the angle of departure. Okay, you just note on this. Now, the root locus branches enter into the real axis with an angle of plus or minus 180 degrees by n. Plus or minus 180 degrees by how many poles and zeros here? 2. Therefore, plus or minus 90 degrees. Like that you can get. Okay. Now, this is the way how to calculate angle of departure and how to draw the root locus diagram for a complex conjugate poles are available in the transfer function. Now, the transfer function g of s, which is equal to k into s square plus 2s plus 2 by s plus 2 into s plus 4. Now the same situation here, but now this is complex conjugate zeros. Same situation, but this is complex conjugate zeros. Minus 1 plus j1 minus 1 minus j1. Okay. And these are the normal poles, minus 2, minus 4. Now this is the root locus branch. Now the root locus branch starts at poles but terminates at complex conjugate 0. Now with some angle. Now this angle is called as angle of arrival. Angle of arrival. So now first we want to find angle of arrival. What is angle of arrival? Theta A. Angle of arrival. This is the angle at which the root locus branches terminates at complex conjugate 0. And the angle of arrival is calculated at complex conjugate 0. And same problem, same procedure. Now this is the theta A. Now measure all the angles made by, some of the angles made by poles and some of the angles made by zeros with respect to complex conjugate 0. Now, so we'll do that first. Now this angle to this complex conjugate 0, this is the angle made by 0. And this is the angle made by pole P1. And this is the angle made by pole P2. Now these are the angles made by poles and these are the angles made by zeros. Now sum of the angles made by poles, which is nothing but same. Now what about this vector distance? Phi P1, which is nothing but tan inverse. This distance is 1 by 1, which is equal to 45 degrees. Now what is phi P2? Phi P2, which is nothing but tan inverse. This distance is 3. This distance is 1 by 3, which is nothing but 18.43 degrees. Therefore, sum of the angles made by poles, pi P1 plus pi P2 minus sum of the angles made by zeros. Therefore, now this is nothing but 45 degrees plus 18.43 degrees minus 90 degrees. Therefore, minus 26.57 degrees is the phi. And now this is the angle of arrival, arrived angle, in angle, additional angle. Now this is 180 degrees plus phi is the angle of arrival. So the angle of arrival, which is nothing but the angle of arrival theta A, which is equal to 180 degrees plus phi is minus 26.57 degrees. Therefore, 153.43 degrees is the angle of arrival. Note down that. Okay. Now this is the way how to calculate angle of arrival, and because sometimes he is asking what is angle of arrival and what is angle of departure, like that also he is asking the question. Now you can easily draw the root locus diagram. Now these are the complex conjugate zeros. -1 plus j1 -1 minus j1, and there are poles at -2 and -4. This is the root locus branch, right? Now root locus diagram starts with k equals 0. The root locus diagram starts with k equals 0. Starts with open loop pole. Starts with open loop pole. As k is changing, closed loop pole is moving. As k is changing, closed loop pole is moving. And the root locus diagram, as k is changing, closed loop pole is moving. And these two closed loop poles are meet at a particular point on the real axis. Now with what angle? Plus or minus 90 degrees. With plus 90 degrees, with minus 90 degrees. And the root locus branch terminates at complex conjugate 0 with an angle of arrival. Therefore, it leaves the real axis and terminates at complex conjugate 0. Leaves the real axis and terminates with complex conjugate 0. Now, with leaves the real axis and terminates at complex conjugate 0. Now, this is called as angle of arrival. This is called as angle of arrival. Same. Now, here you want to find break away point. Here you want to find breakaway point, and what is the system gain k at breakaway point. Now if you observe, these two root locus diagrams shape is same because I am doing the same problem. I just change numerator to denominator, denominator to numerator. That's why you can get the same answer. Angle of departure equal to angle of arrival, and breakaway point equal to break-in point. Gain at breakaway point equal to gain at break-in point. These should be similarities because I just interchange the numerator to denominator, denominator to numerator. But don't think that angle of departure, angle of arrival same. It is the procedure of calculating departure and arrival. Okay, just note down this.